Alright, now that we started to build an intuition, develop some understanding about vectors, let's talk about some of their algebraic properties. Okay. I'm just going to go down the list of some of their algebraic properties, what they're called, and give you a quick example using the vectors that we have right here, u, v, and w, and using the constants, the scalar multiples d and c. Alright, so let's start at the top. So our first property, okay, is the commutative property of addition. Okay, and that's really just saying u plus v is equal to v plus u, right? So you can just switch them very easily and they equal the same thing. So 1 plus 3, that's what u is, plus what did we define as v? We defined it as 1 plus 2 is equal to what? That's equal to 2, 5. If we switch these around, what do we get? Right, so this is u plus v. Here comes v plus u. Now we get 1, 2 plus 1, 3. We get, look at that, it's 2, 5. Alright, so now what we have is the next, what we're going to look at is we're going to look at the associative property. Associative property of addition. Alright. And that just basically states that u plus v plus w in parentheses is equal to u plus v in parentheses plus w. Okay? So basically, if I have, sorry about that. One, and we said 3 plus, and we put this in parentheses, 1 and 2. Okay. Plus, what do we define as w? We define w as 2, 1 is equal to, well, let's think about it. That's equal to 1 plus 3. And then in parentheses, what we're going to be left with is we're going to be left with 3, 3. Alright. And so that is equal to 4, 6. And for the sake of time, I'm going to leave it up to you to verify the other side of this. So now let's keep going. 3, what we have for 3 is a pretty important one, and that is u, or any vector for that matter, plus the 0 vector is equal to, okay, the 0 vector plus u. That's kind of just using the first property we learned, which is just equal to u. Alright, so in our example we have 1 plus 3 plus 0, 0 is equal to, well, what do we get? We get 1 plus 0 is 1 and 3 plus 0 is 3. Look at that. Now moving right along. No, excuse me, this one is called the additive identity, if you want the name of that one. Alright, so now let's look at the next one, and we'll call this one the additive inverse. And what this basically states is that if we have a vector u plus the negative of it, we get the 0 vector. Okay? And that should make some sense, right? So we have 1, 3 plus negative 1. And I'm actually going to write it like this. Yeah, I'll go ahead and write it like this for now. That's fine. 1, 3. These two guys just cancel out, right? We can see, remember that when we do a scalar multiplication, go ahead and that negative 1 is just going to distribute, and then we're basically looking at 1 This is kind of like saying 1 minus 1 and 3 minus 3. Okay. Alright. Moving right along. Now we're going to look at the distributive property. And if you started to notice, right, you'll notice that these are all properties that show up just in basic algebra. Distributive property. Okay. And that's saying C, some constant C times U plus V, alright, is equal to C U plus C V, right? And so what do we have in this case? Well, we said that C is equal to 2, I believe, you know? So we said C is equal to 2, so we have 2 times 1, 3, excuse me, plus we have 1, 2, and that's supposed to be equal to, according to the distributive property, 1, 3 times 2 plus 2 times 1, 2. What do we get with that? Alright, so we get 2, 6 plus 2, 4, and this is going to be equal to 4, 10. And again, I'll leave it up to you to go after that right there and see if this is actually the case. Alright, so moving right along, now we have another property, something a little similar. So what we have here is we have C plus D times U is equal to C times U plus D times U. Alright, so we have C plus DU is equal to CU plus DU, and so what we have here really is this. I'm going to go ahead and work with I'll work with the left side of the equation this time. So that's 2, and D was negative 3, so that's minus 3. Alright, times U we said was 1, 3, and that's going to be equal to negative 1 times 1, 3, which is going to be equal to simply just negative 1, negative 3. So we have negative 1, negative 3, and I'll leave it to you to verify the right side of that equation. Moving along, we have 2 more properties to go over really quickly. So that one is kind of building off the scalar multiplication properties that we've just been building up to right now. And that is basically just CU. Here, let me rewrite this actually, sorry. C, okay, times DU is equal to CD times U. Alright, so what do we have in our example from above? What we have in our example from above is we have 2, alright, negative 3 times 1, 3. What is that going to equal? That's going to equal, so what's on the inside? So what's on the inside? So on the inside we get what? We get negative 3 times 1 is going to be negative 3, and then negative 3 times 3 is going to be negative 9. And then we're going to multiply that by 2. What are we going to be left with when we do that? When we do that, we're just going to get 2 times negative 3 is negative 6, and 2 times negative 9 is negative 18. Again, I'll let you go ahead and verify that right side. Now our last property is a pretty straightforward one. And that really just is 1 times u, excuse me, do it in the proper color, or again, any vector is just equal to that vector, right? So 1 times any vector is just equal to the vector. It's the same thing as when we multiply 1 times a number, right? That one's almost so trivial it doesn't even make sense to write it out, but I'll go ahead and do it just because, all right? And this is equal to 1, 3, right? It's just equal to itself. All right, so that is a kind of introduction to some of the algebraic properties that we see in vectors in any dimensional space. R2, R3, Rn, doesn't matter. And don't worry too much about memorizing these because they really stem from just generic algebra properties that you'd see that you get with multiplying with numbers. So if you're comfortable with those, you'll be comfortable with these.